built across the Blue Nile, a $5 billion wall of concrete designed to transform the energy future of an entire nation. This is the Grand Ethiopian Renaissance Dam, a massive hydropower system containing more than 10 million cubic meters of roller-compacted concrete, with enough generating capacity to produce 5,150 megawatts. But the dam could not begin with concrete. First, engineers had to move the river. They had to expose a stable foundation beneath the water, survive the return of the rainy season, produce concrete at industrial speed, and close a second opening through the surrounding landscape. For 14 years, the project tested Ethiopia's engineering capacity, financial endurance, and national determination. This is how Ethiopia built one of Africa's most ambitious power projects across a river that never stopped moving. The Grand Ethiopian Renaissance Dam, better known as GERD, stands on the Blue Nile in Ethiopia's Benishangul Gumuz region, near the border with Sudan. From downstream, the main structure appears almost impossible to miss. A vast concrete gravity dam stretches approximately 1.8 kilometers across the valley and rises about 170 meters from its structural foundation. But the wall is only the visible center of a much larger machine. At its base are two hydroelectric powerhouses. Inside them, 13 Francis turbines convert the force of falling water into electricity. Behind the dam lies a reservoir with a reported storage capacity of approximately 74 billion cubic meters. Multiple spillways protect the structure during periods of high inflow. Intake systems, pressurized waterways, transformers, transmission equipment, internal galleries, and monitoring instruments allow the entire complex to operate as one connected system. And even this enormous main dam was not enough to contain the future reservoir. Several kilometers away, engineers would eventually need to build another barrier across the landscape. GERD was never one structure. It was a complete river control and power generation system spread across an entire valley. For Ethiopia, the project began with electricity. The country possesses major hydropower potential, but millions of people have historically lived without reliable access to power. Electricity is required for far more than lighting homes. It supports factories, hospitals, water systems, communications, transportation, schools, and the industries that create jobs. GERD was designed to expand Ethiopia's generating capacity and create additional power that could also be exported to neighboring countries. The Blue Nile offered the basic conditions required for a giant hydropower project: a large volume of moving water, a landscape capable of holding a vast reservoir, and enough elevation difference to turn gravity into usable energy. Water stored high behind a dam contains potential energy. When that water descends through a controlled passage, it accelerates. The moving water turns a turbine. The turbine drives a generator, and the generator produces electricity. The principle is simple. Building the system at the scale of GERD was not. Before Ethiopia could capture the river's energy, engineers first had to create a place where construction could survive it. The Blue Nile could not be switched off while the dam was being built. During the dry season, its flow was lower and more predictable. But when the rains returned to the Ethiopian highlands, the river transformed. Water levels rose. Current speed increased. Sediment and debris moved downstream. And temporary structures that appeared secure during the dry months had to survive an entirely different river. At the same time, the remote project site needed roads, bridges, workshops, power, accommodation, medical support, laboratories, storage areas, and a constant supply of fuel, cement, steel, and machinery. This meant Ethiopia first had to build infrastructure for the construction project before the permanent infrastructure could rise. The site gradually became an industrial settlement organized around the changing rhythm of the Nile. Every major operation had to fit inside a narrow seasonal window, excavate too slowly, and the rains could return before the work area was protected. Place concrete too late, and the next flood season could interrupt the sequence. The river did not adjust to the construction schedule. The construction schedule had to adjust to the river. The original diversion strategy called for engineers to build large culverts while the Blue Nile continued flowing through its natural channel. During a dry season, the river would be directed through those culverts, opening the central gorge for construction. But excavation revealed a more difficult riverbed than expected. The gorge was deeper, and extensive sediment lay beneath the channel. The original plan had to change. Engineers introduced an additional diversion channel on the right bank. This required approximately 2.5 million cubic meters of rock excavation, together with cofferdams and walls to guide the flow. This was not a minor correction. River diversion controlled the entire schedule of the project. Until the water moved, foundation work could not fully advance. Until the foundation was prepared, the central dam could not rise. And until the central structure reached a safe level, it remained vulnerable to the next wet season. During lower flow periods, 4 large diversion culverts could carry water through the work zone. When the wet season brought flows beyond their capacity, a temporary stepped spillway within the growing dam allowed water to pass over a controlled section of the structure. The Blue Nile was not redirected in one dramatic moment. Its route changed as the construction sequence changed. Engineers built around the river, moved it through temporary passages, and allowed it to cross sections of the rising structure when seasonal flows became too large. GERD did not begin by stopping the Nile. It began by repeatedly creating space inside a moving river. Once water was moved away from part of the site, crews could reach the future foundation. A gravity dam resists reservoir pressure through its enormous mass. That mass must transfer safely into stable rock. Weak material, loose sediment, and weathered surfaces therefore had to be removed before permanent concrete could be placed. The exposed foundation was cleaned, inspected, and treated to control water moving beneath the structure. Internal drainage and monitoring systems were incorporated so engineers could track pressure, seepage, temperature, and structural movement after the reservoir began to rise. Most of this work would eventually disappear. The prepared rock would be buried beneath the dam. The instruments would remain hidden inside it. But the safety of the completed structure would depend on these invisible systems long after construction ended. Only when the foundation was ready could GERD's central construction machine move into full operation. The main dam required approximately 10.7 million cubic meters of roller-compacted concrete, known as RCC. RCC is different from the fluid concrete commonly pumped into columns or building floors. It contains less water and has a much drier consistency. That allows it to be transported in large quantities, spread in horizontal layers, and compacted by heavy rollers. For a gravity dam, this creates a major advantage. The structure does not need to rise through thousands of small conventional pores. It can be built through a continuous industrial cycle, but that cycle begins long before concrete reaches the dam. Rock must first be extracted from quarries. It is crushed into carefully controlled aggregate sizes. The aggregates are screened, stored, and delivered to batching plants. Cementitious materials and water are measured into each mixture. The finished RCC must then travel to the placement area before its working time expires. At the dam, machines spread the material across a prepared surface. Rollers compact it into a dense layer. Technicians test moisture, density, temperature, strength, and consistency. Surveyors confirm position and elevation. The surface is prepared for the next placement. Then the cycle begins again. Mix, move, spread, compact, test, repeat. Every part of this chain had to stay synchronized. If aggregate production slowed, the batching plants could run short. If transportation failed, fresh RCC could not reach the placement area. If compaction fell behind, the quality of the layer could be affected. If the next lift arrived too late, bonding between layers would become more difficult. The project developed specialized RCC mixtures with longer setting times. This gave the construction system more flexibility while helping maintain material quality. This mattered because GERD was not placing concrete at the pace of an ordinary structure. On December 28, 2014, the construction site reportedly placed approximately 23,000 cubic meters of RCC within 24 hours. For that single day to succeed, quarry crews, crushing plants, batching systems, transport equipment, placement teams, rollers, laboratories, surveyors, mechanics, and power supplies all had to operate without losing the production rhythm. This was the real scale of the dam. Not just its height, not just its length, but the enormous industrial system required to make the wall rise one compacted layer at a time. Rock entered the system at one end. A permanent section of dam emerged at the other. As the main concrete wall rose across the Blue Nile, another problem remained several kilometers away. The surrounding terrain contained a natural low point. Once the reservoir climbed toward its operating level, water could move through this depression and escape around the main dam. The solution was a saddle dam. Unlike the RCC structure in the river channel, the saddle dam was built mainly from rockfill and protected by a concrete face. The mass of compacted rock provides stability. The concrete facing forms the primary water barrier. Stretching approximately 5 kilometers across the landscape, the saddle dam was far longer than the main concrete structure. Its size demonstrates an essential principle of reservoir construction. Engineers do not only dam the river, they must also study every surrounding ridge, depression, and possible escape route below the future water level. The main dam closed the Blue Nile Valley. The saddle dam closed the landscape around it. Only together could they contain the reservoir. Holding water is only one part of dam engineering. The structure must also release water safely when inflow becomes too great. If the reservoir rises faster than water can pass through the turbines and normal outlets, it approaches the dam's maximum operating level. Without sufficient spillway capacity, uncontrolled overtopping could threaten the structure. GERD therefore uses several discharge systems. A gated service spillway allows operators to control major releases. A free-flow stepped spillway passes additional water over a designated section of the main dam. An emergency side-channel spillway provides another route during exceptional conditions. But opening a path is not enough. Water descending from the reservoir gains enormous speed and destructive energy. If that energy is not controlled, it can erode the riverbed and damage the area near the dam's foundation. The stepped surfaces and downstream energy dissipation structures break up the flow, reduce its energy, and guide it back toward the river channel. The dam was designed to resist the Nile. Its spillways were designed to cooperate with it. A dam survives not only by holding water back, but by knowing when and how to let it go. The reservoir stores water at elevation. Controlled intake structures allow that water to enter large pressurized passages embedded in the dam. As the water descends toward the powerhouses, gravity increases its energy. The flow reaches the blades of a Francis turbine and forces the runner to rotate. That rotating shaft drives a generator. Transformers then raise the voltage, allowing electricity to travel efficiently through the transmission network. After passing through the turbines, the water returns to the Blue Nile downstream. GERD's 2 powerhouses contain 13 Francis turbine units with a combined installed capacity of 5,150 megawatts. The completed plant was designed to generate approximately 15.7 terawatt-hours of electricity during an average year. But generating capacity is not the same as electricity delivered to a home. Power must still travel through high-voltage lines, substations, and distribution systems before it reaches communities and industries. GERD created an enormous new source of energy. The wider electrical network determines how far that energy can travel. The reservoir stores the potential, the turbines release it, and the grid carries it beyond the river valley. Even after the concrete structures were largely complete, GERD could not begin operating at full capacity immediately. The reservoir had to rise gradually. Sufficient water elevation was needed to create the pressure required for generation. Each turbine also had to pass through commissioning. Mechanical systems were inspected. Rotating components were tested. Engineers monitored vibration, temperature, water pressure, lubrication, and electrical protection. Generators had to synchronize with the grid before their output could increase. The first GERD turbine began producing electricity in 2022. Additional generating units entered service progressively as the reservoir level and electrical systems advanced. The completed project was officially inaugurated on September 9, 2025. Its final configuration,
The intake
13
readings are
turbines
stable
and
and within acceptable
5,150 megawatts,
Noted.
differed from
Continue
earlier
monitoring the
project
flow rates
plans
and reservoir
that had
levels.
described a
The
larger
runner
number of
surface looks
generating
pristine,
units.
ready for
Mega
rotation.
projects
Check the
evolve.
bearings, no
Designs
issues found.
change as construction
Status report for the
conditions,
control room.
equipment decisions, operating requirements, and project priorities become clearer. Finishing the concrete was a major milestone, but the project became a functioning power station only when water, turbines, generators, protection systems, and the national grid could operate together. GERD is widely reported to have cost approximately $5 billion. For Ethiopia, raising and sustaining that investment became part of the engineering challenge. The project was financed largely through domestic resources, including government funding, bonds, and public contributions. But money alone could not build the dam. For 14 years, the remote valley had to support an enormous workforce and a continuous industrial operation. More than 25,000 people reportedly participated over the life of the project, most of them Ethiopian. Roads, bridges, workshops, medical facilities, accommodation, schools, and production services transformed the area around the construction site. Quarry workers produced aggregate, drivers moved materials, mechanics kept heavy equipment operating, laboratory teams tested concrete, surveyors measured the rising structure, electricians, engineers, safety teams, medical staff, and thousands of construction workers kept the project moving through dry seasons, floods, design changes, and years of uncertainty. The human achievement was not contained in one dramatic moment. It existed in repetition. Another shift, another layer, another inspection, another repair completed before production stopped. The dam is measured in meters, cubic volumes, and megawatts, but it was built through millions of coordinated decisions made over more than a decade. When GERD was inaugurated, Ethiopia had largely answered the construction question, but the Blue Nile does not end at the dam. It continues into Sudan and eventually contributes to the Nile system on which Egypt heavily depends. Ethiopia presents GERD as a hydropower project intended to support development and regional electricity trade. Egypt remains concerned that reservoir operations could affect downstream water supplies, particularly during a prolonged drought. Sudan has called for coordinated operating rules, while also potentially benefiting from more regulated flows and access to electricity. The central dispute is not simply whether water continues downstream after passing through the turbines. It is about timing. How quickly should the reservoir rise? How much water should be released during severe drought? What information should be shared? And what rules should bind the countries using the same river? Engineers could design the spillways and calculate the pressure inside the dam. They could not determine how three nations should share the risks of an international river. The structure is complete. The operating question continues downstream. The Grand Ethiopian Renaissance Dam began with an extreme engineering problem. How could Ethiopia build a continental-scale power system while the Blue Nile continued flowing through the construction site? The answer came through river diversion, deep excavation, foundation treatment, industrial concrete production, flood control engineering, turbine installation, and 14 years of human determination. The river was repeatedly moved. More than 10 million cubic meters of RCC became a permanent gravity structure. A second dam closed an opening in the surrounding landscape. Multiple spillways created safe paths for extreme water, and 13 turbines transformed the stored force of the Blue Nile into electricity. GERD is more than a concrete wall. It is a machine embedded in the Ethiopian highlands, one capable of reshaping the country's energy future while linking that future to every nation downstream. This is where concrete meets the Blue Nile, where national ambition becomes physical infrastructure, and where impossible engineering becomes a responsibility shared across an entire river basin.